I'm Avik, and today I'm going to talk about my work on uncovering privacy leakage in Bluetooth low energy networks in fitness trackers. This work is done with a postdoc in my group, Parth Pathak, and my two advisors, Professor Chua and Professor Mahapatra. So this is going to be the overview of what I'm going to talk about today. We're going to introduce BLE, the standard, and we're going to talk about the motivation, followed by leakage using data packets. We're going to talk about a few prevention strategies that we thought about, and that then we can conclude the paper, conclude the talk. Okay, so we all know what increasingly popular because of the notion of the quantified self, where users can track how many steps they take, how many miles they walk, how many calories they burn, etc., etc. But from BLE, BLE is becoming the dominant standard that is used for communication between these fitness trackers and our smartphones. So just a little statistics, like there's been a 200% growth in the shipping of fitness trackers between 2014 to 2015. Expect that to grow even further. So we have seen a lot of works, like very recent works, which has looked at how to track users' hand motion or users' gestures from the raw sensor data in these trackers. But what we are focusing on in this paper is slightly different from focusing on the leakage that is happening in the network data, in the communication between the phone and the fitness trackers. Whatever leakage is happening, we are doing a measurement study of that, and we are presenting some results. Okay, so I'll just introduce the BLE standard slightly because we are going to have parts of the talk based on that. So first up are the advertising packets, but the most important thing that we focus on is the undirected connectable advertising package, which is basically broadcast packets from all these fitness trackers, and which are sent out continuously. Whenever the phone is not connected to the fitness tracker is constantly broadcasting. Also, these packets include the MAC address of the fitness tracker and also includes the local name, which basically reveals the company or the type of the fitness tracker. Like it tells you it's a Fitbit Charge or a Fitbit Flex or something like that. So as you see in this picture, the advertising packets are sent out, followed by a scan request, followed by a scan response, and then we have a connect request, after which the connection actually happens. And we move from advertising packets to data packets. So one of the few things that the BLE standard recommends is a private advertising address so that you cannot track users based on a MAC address that's always constant. So they suggest to use non-resolvable private addresses, which are basically where your address randomly changes to a temporary identifier after some certain intervals of time. Or they suggest you to use resolvable private address, which is basically something that can be resolved using a key and a random number that is generated. And there's the third one, which is a static address, which they suggest to be changed at boot up or never changed. And like that is where our privacy is getting leaked when a static address is being used. So we'll talk about that when we get there. That was advertising packets. Next is data packets. So once a data connection has been established between a smartphone and a wearable, there are an exchange of data packets over the 37 data channels through adaptive frequency hopping. Most of the data communication, that is the sharing of payload, happens in the start and the continuation packets, where like actual data transfer is happening. Empty packets are sent out just to maintain the connection between different hops. We have seen that the smartphones connect periodically, as I said, and the peripherals advertise constantly when it's not connected to the smartphone. Okay, so since this is basically a network-based measurement study from which we are detecting privacy, the first and most important thing is data collection. So what are the two main conditions that we had for selecting a sniffer? Is it has to sniff on all the three advertising channels simultaneously, and it also should follow the connection in all the 37 data channels once it goes into connect mode. So we see that the frontline Comprobe BPS 600 is very useful in doing that. It does exactly what we want. And using that, we can inspect each and every packet and all the fields of the packet. Like you can see, we can see the type of the packet, we see the advertiser address, and we also see the local name, which is telling us that it's a Misfit Shine. It's one of the devices that we use. Okay, so now looking at the BLE privacy leakage, and we will go with advertising packets first, the leakage of which is user tracking. So how this works is a very, like, the since the fitness tracker is constantly advertising, constantly broadcasting, any third-party sniffer can sniff these advertising packets and from there track a particular device if the device is not changing its address. And based on this device information and some auxiliary information that we might have, like key swipes or some video camera recording, we can attach each device to a particular user and we can detect the user. So now the question comes is, does these devices actually change their addresses or not? So we verify that based on two data sets that we collect. The first is the controlled experiments that we do in our lab, where we use 6 leading fitness trackers that we buy off the market and power cycle them and collect data on different days, different locations, different power cycles, and we see that even after all these things, their addresses remain exactly the same for all the 6 devices. So, which means that if they're not changing their addresses, if I wear that device to any location and that location has a sniffer, they can identify that I have been visiting that location from exactly this time to this time every day, or whichever days I go at. The next data set that we use is a gymnasium data set where we collect data for 8 days, 2 hours per day, and we got a lot of advertising packets. Using those advertising packets, we identify the fitness trackers based on the local name that we saw in that snapshot of the data collection. So we get like 99 unique fitness trackers that we see, and there's just a simple representation of the common ones that we observe. And we also observe that the smartphones are not advertising at all. All the smartphones do is send out scan requests, and that too they change their addresses after certain intervals. Like it's not a constant addresses being sent out by smartphones. So based on the data set that we see, most of the devices use the static address that we talked about at the very beginning, which is not changing its addresses at all. And around 25% of the fitness trackers are there in more than one trace, which is a big deal because here the traces are collected on different days and not at the same time every day. So that means 25% of the device users are coming back at the location of multiple, like during the time we are collecting the trace. And that is basically can lead to be those users being tracked because of their addresses not altering. So that's the point of view of user tracking from the advertising packets. Next, we look at privacy leakage from the data packet point of view. For that, I'll first explain our experimental setup, which is basically data collected through 10 volunteers, each wearing a Fitbit and a Nexus 5 on their wrist. And we collect data for 10 times 150 seconds each. And we also collect the network data based on the connection between a Fitbit and an iPhone 6. And the user is asked to do 4 different activities: walk, run, sit idly, and sit and work on the computer. So the data packet's privacy leakage has 2 dimensions to it. The first one that we look at is activity detection. So the BLE traffic that we collect is encrypted. We are not looking at the payload of the traffic in any way. But what we find out is that the data rate is proportional to the user activity. Like the more intense your activity is, the more amount of data is being transferred between your smartphone and your fitness tracker. So using very basic features like data rate, start, and empty packets, we get activity identification at a very high accuracy. If you look at these 4 graphs for the 4 different activities of one particular user, you can see that as the intensity is more, the amount of data that is being transferred is drastically high, which is telling us that looking at different time periods of these data, we can actually identify what a user has been doing in that time period. So that was the activity detection point of view. Now the same thing can be extended to detect a particular person. So this can be used in a scenario where there's a small set of users, like an office or a personal, like a gym of, like house gym or something, where there are a fixed set of users for whom the system has to be pre-trained in this case. So we see that the accelerometer readings that is being collected by the Fitbit, which we here collect using the Nexus 6 that is attached to the wrist, is correlated very highly with the Bluetooth network traffic statistics, like the data rate and the packet sizes and the number of packets. And we have seen a lot of papers, and we know that different users have different gait, which can be used to identify different users. So since the different activity intensities can be identified using the BLE network traffic, we also believe that users' gait and motion can also be identified using the BLE network traffic. So we use some features like data rate, and the number of packets, payload sizes, interval between packets on the 10 volunteer list that we had, and we got around 89% accuracy for 5 people groups. We saw that after 5 people, the accuracy drops down to around 59% for 10 people. That is because the more is the number of users, the difference in their activity, becomes, like the difference becomes less. So as a result, it's more difficult to, distinguish them. So as I said, this can be possible when the users have been trained and it works in a office or a small gym. So those were the two attacks based on the advertising packets as well as the data packets that we looked at. Now we suggest some possible prevention strategies based on other works that have been done in network, like mostly Wi-Fi network. One thing is randomized MAC address as per the standard. The problem there that we perceive is if we randomize the address, it's going to be very difficult for the smartphones to actually identify these fitness trackers to which it has already been paired. So then the pairing or a more number of communication has to be done again to pair the smartphone or to identify which smartphone it's being paired to. So that's from the advertising packet point of view. From the data packet point of view, it's a pretty simple solution where you can include some artificial data or SHAF in the data package so that the data rate is no longer proportional. Like you send some garbage traffic just so that it's not always proportional to the activity. The major problem that is it can lead to higher power consumption because you're increasing the payload size. But overall, because of IoTs and smart homes and smart cities becoming so popular, we believe that Bluetooth network privacy is something important and worth looking at, and that's why we did this work. So these are the references that we discuss in the paper and that we look at, and with that, I would like to conclude my talk.